Hello everyone, welcome to this talk on our paper titled GraphPulse, an event-driven hardware accelerator for asynchronous graph processing. I am Shafiur Rahman from University of California, Riverside. Computation on large graph is an important computational workload in many modern-day computing. Many important domains depend on graph analytics to uncover insights from high volumes of connected data, such as social network, web graphs, recommendation system, bioinformatics, and many others. So there is a growing demand for efficient graph analytics frameworks for large graphs. Many important applications depend on some common types of graph algorithms, such as PageRank, adsorption, breadth first search, connected components, etc. We can take advantage of graph analytics frameworks to easily implement these algorithms in an optimized way. Most graph analytics frameworks adopt a vertex-centric processing approach. This vertex-centric or think like a vertex approach needs to access each neighboring vertices when processing a vertex. The neighbors are not located closely in memory and the data dependence is dynamic, thus creating irregular memory access pattern. The accesses cannot be predicted beforehand for effective prefetching. Coupled with the low computation to communication ratio, vertex-centric processing suffers from significant memory inefficiencies. Traditionally, these inefficiencies are solved using on-chip caches, but most graphs are too large with negligible locality to get any benefit from the small caches in conventional system. Here, we look into the memory access pattern for a push-based vertex ordered program. The scheduler loops through each vertex. For each vertex, the processor needs to read and modify vertices on outgoing edges, creating costly random accesses. This also requires the use of atomic operation for parallel systems, which has added overhead. In another approach, the pool-based computation, the scheduled vertex needs to read data from all vertices on the incoming edges. This creates a lot of random reads. The cost for random writes and atomic operation can be avoided, but the program read states from many vertices that weren't updated after last iteration. This creates a lot of redundant memory reads. Hardware accelerators try to enhance performance of the graph processing frameworks by optimizing the memory latencies. Some typical methods are providing special primitives for efficient atomic operation, crafting specialized pipelines using on-chip memory as large dedicated caches, and so on. However, the hardware implementations following think like a vertex approach still suffers from the same inefficient memory access pattern as in software. They have heavy dependence on the graph structure and limited control over the access pattern. Thus, dependence on the execution model makes them unable to take full advantage of the capabilities of the hardware. Hardware accelerators perform better when they act on a data flow style execution as opposed to the control flow style execution of the vertex-centric processing approach. We believe that a specialized execution model suitable for hardware is necessary to make the best use of hardware capabilities. The execution model is based on the idea that the memory accesses for a vertex can be separated from the communication of neighbor states to achieve a streamlined data flow execution. The first implication is that each vertex accesses and updates its own properties only. This will eliminate the random accesses of neighbors' data. The memory access pattern is much simplified as a result. Also, it simplifies ensuring transaction safety during parallel processing. The second component is that any updates pushed to the neighbors will be sent as messages. However, we can use these messages for managing scheduling of vertices, thus converting the messages to events. One benefit comes from the fact that the extra overhead for active set maintenance is eliminated, since the events will represent the active computations of the graph. Moreover, fine-grained scheduling of the vertices are possible by manipulating the events. Let's take this example where we want to find the shortest path from the root A of the given example graph. The pseudocode is on the left. The pseudocode is same for all graph algorithms. The user needs to define the initial vertex states, initial sets of events, a reduce and a propagate function, and a condition to stop propagation of updates. For SSSP, the graph states are initialized to infinity, and we place a single event with payload 0 targeted for vertex A, which is the source for SSSP. The algorithm starts and the first event is popped from the queue. We update the target vertex using the reduction function. For SSSP, the reduction function is a minimum operation. The update changes the state of A, so we propagate the change to its neighbors B and C using the propagate function. For SSSP, the propagate function is the summation operation on the vertex state and the edge weight. Similarly, these events are popped to give rise to new set of events. B will be updated again from 5 to 4 because another path through C delivers a shorter path. We will notice that the event to D with payload 9 has a longer path than D's current state 8. So this event will not be propagated. The execution goes on like this for several more iterations until all the events in the queue stops propagating and the queue is empty of new events. The application terminates at this point and the state of the graph is in the valid converged state. In this execution model, each vertex only reads and updates its own data only. The neighbor's information is carried through the event. This isolates the memory access to the target's vertex's memory. Since processes don't access neighbors' vertices at random, locking or atomicity becomes much simpler. Additionally, the memory access pattern doesn't depend on the graph structure anymore, but on the sequence of events on the queue. However, the events target random vertices, resulting in random memory accesses. Also, parallel operation may still need locking because two events targeted to same vertex may get scheduled to two different processors at the same time. To reduce random accesses, the events can be ordered in the queue based on their target vertices. When issued in this sorted order, the memory accesses will be sequential and predictable. Even partial sorting will result in significant spatial locality. Sorting of the event is possible in many graph algorithms because the reduce function is commutative and associative. This means that the events can be reduced with the vertex states in any order while maintaining correctness. The capability of reordering events in queue gives more control to find a scheduling policy to optimize memory access. Another problem appears in this execution model from the rapid growth of the number of events in the queue or the event population. Each event processed usually propagates along all its edges and creates set of new events. Thus, the rate of consumption of events is much less than the rate of generation of events. This creates exponential rise in the event population. For parallel graphs, the memory system will be quickly overwhelmed to accommodate this massive number of events. For algorithms like PageRank, initially almost all edges create an event in each iteration, thus making the event population grow towards the total number of edges in the graph. The plot on the left shows the event generated in each iteration for PageRank algorithm in LiveJournal graph. Since there are multiple events destined to the same vertex in the queue, we can combine them together to reduce the number of events in the queue. When all events for a vertex is coalesced to only one event, the total number of events in the queue becomes bounded by the number of vertices. This reduces the maximum queue population significantly. The plot on the right shows the total events remaining after each round after coalescing of the events. Coalescing works because the propagation function for many graph algorithms will have distributive property over the reduction function. This means that the program maintains correctness even if the propagation function is applied to two events already reduced together instead of propagating them separately. As a result, multiple events can be merged safely while in the queue. The effect of the coalescing is significant in the performance of the system. Since event schedule vertex and only one event remain after the coalescing, we can guarantee that the processor will never have contention for the same vertex. This enables the system to avoid locking or atomic operation completely for parallel execution. The scheduling is much more relaxed as a result, and massive parallelism can be exploited. Additionally, the events take less storage and becomes easier to maintain. Lesser number of events mean less processing tasks, and the effect of coalescing compounds on each iteration. Finally, when two events are reduced even before reaching a vertex, the vertex updates with their combined effect and reaches convergence faster. We define two properties for a graph to be effective with event-driven execution model. First, the reordering property allows events to be sorted and coalesced. The reordering property requires the reduction function to be commutative, associative, and distributive, and the propagation function must be distributive over the reduced function. The simplification property allows the events to stop propagation and terminate the algorithm. The property requires a vertex should not have any impact on its neighbor when it doesn't change. Many popular graph algorithms include these two properties, such as incremental PageRank, adsorption, SSP, BFS, connected components, and many linear equation solvers. The requirements for event-driven execution may seem trivial, but they have significant challenges when implemented in software. The sorted queue implementation is very expensive in software, and the coalescing in software comes with a huge overhead. Also, an efficient scheduling policy implementation may come with significant complexity in software. GraphPulse provides hardware primitives to mitigate these challenges. GraphPulse is an asynchronous graph processing accelerator that leverages the benefits coming from decoupling of Vertex updates and the Vertex communication to maximize memory access efficiency and increase parallelism by using a data flow execution. Next, we discuss the architecture of GraphPulse accelerator. The main components are the event queue, event scheduler, and the event processors. The event queue has the capability of efficiently coalescing events in place. The events are direct mapped to the on-chip memory like a direct mapped cache. The queue is fitted with coalescing pipeline, performing reduce operations during insertion of events. The queues contain multiple beans for parallel insertion and dequeuing. The event scheduler gets events in bulk from the queue and distributes them to the idle processors in a memory access-friendly scheduling policy. It buffers events from the queue to minimize the idle time of the processing cores. It schedules memory adjacent vertices to one processor so that memory can be accessed more efficiently. The event processors update the vertex states after receiving the events. It includes an accurate prefetcher that reduces the average memory access latency. Events indicate the vertex to be accessed and the target vertices can be accurately prefetched. The event processor also employs parallel event generation units to saturate the DRAM bandwidth. We evaluated GraphPulse on a cycle-accurate simulator based on structural simulation toolkit. The simulation was done for 1 GHz clock and 64 MB of on-chip memory. We compared the performance with state-of-the-art software framework Ligra running on Intel Xeon processor with identical DRAM memory channels. We also compared with a previous hardware graph processing accelerator, GraphPulse, that has same clock, on-chip memory and off-chip memory system. We ran the evaluations on 5 real-world large graph using 5 common graph processing algorithms. The plot shows the performance of GraphPulse and GraphPulse normalized over the performance of state-of-the-art software framework Ligra. GraphPulse achieves about 28 times speed up over the software. The performance for GraphPulse is about 6.2 times better on average than GraphPulse. The event-driven execution model of GraphPulse has an execution pattern that is more efficient than conventional models because of coalescing and locality-aware scheduling. The plot shows the total off-chip memory access of GraphPulse compared to the hardware accelerator GraphPulse. Even compared to the optimized access pattern of GraphPulse, GraphPulse memory accesses are about 54% less on average, giving good speed up to GraphPulse. Additionally, due to accurate prefetching and memory access-friendly scheduling policy that GraphPulse implements, GraphPulse avoids unnecessary reads from the DRAM memory. The plot shows the fraction of data pulled from off-chip memory that was used in useful work. GraphPulse utilizes about 75% of the accessed off-chip memory on average. Finally, I will invite everyone to read the paper for more details on the execution model and the architecture. Moreover, the paper includes more details on partitioning and scaling techniques for large graphs. It has several more evaluation results and the area and energy estimate for an ASIC implementation for the accelerator. In conclusion, we see that the event-driven processing model eliminates major memory bottlenecks in graph analytics. It has fine-grained control over scheduling, lock-free memory access for extensive parallelism, and hardware-friendly abstraction. GraphPulse provides an efficient architecture for event-driven graph processing model. It allows efficient event coalescing to control event population and faster convergence. It has optimized prefetching strategies to saturate memory bandwidth. GraphPulse employs an efficient memory access pattern for maximum utilization of DRAM accesses. The effects of these can be seen on the performance evaluation. GraphPulse has 28 times better performance on average compared to software frameworks and 28 times energy reduction compared to conventional CPU platforms.